Hello, this is Paul from Foresight Tech, and this video let's prove Theorem 1.5.2, which is the inverse of elementary matrices. The theorem says every elementary matrix, okay, we have three types, right? Each type is invertible still, and the inverse is also an elementary matrix. And let's also find what is the inverse matrix. Okay, see. I will verify it. Okay, so by just use 3 by 3 matrix. See, let's simply verify using 3 by 3. Let's say a matrix E is 3 by 3. Okay, so E is 3 by 3. We have 3 types, so I verify type by type. Verify type 1. Okay, let's see. Which matrix type 1 is this matrix. Let me give an example. Like I times k to the second row. Okay, so here is k, here is 1, here is 1, okay, 0. Now let's find what is the inverse of this matrix. How to find the inverse of matrix? The inverse matrix should be times this matrix equals identity, right? Okay, and that's multiplication. Remember the previous theorem we say multiplication we can change it into row operation, or row operation we can change it into matrix multiplication. So we try to use that. So let's go row operation first. We need to get an identity. So I, which is 3 by 3. What kind of row operation? Still the first type of row operation. Let me write should be multiply the second row by 1 out of k inverse of k, right? See? Okay, that should be the row operation. This row operation we can find a corresponding elementary, which is this, right? Okay, and then by the theorem, okay, and then by the theorem, the previous theorem, okay, 1.5.1. Okay, so we have this result. See, this is E. Okay, and if we want to get the identity, we just multiply E to the left. Okay, left multiply E, okay, to the matrix, and this matrix I can find the identity. Okay, let me write the equation. Yeah, so this is the equation. Oh, sorry, I made a mistake. So here is not 0, it's 1, right? Okay. Can you see? This row operation we change to matrix multiplication. The previous theorem 1.5.1 says this. Okay, so from here I get a result. What kind of result? I know the first matrix, see, this matrix is the inverse of this matrix. So therefore, we find that the inverse matrix of this, the first type of elementary, so the other first type of elementary, okay. Just what? Just get an inverse of this k, okay, flip the k. So let me write down the result. Okay, so that's the first. The first type of elementary is invertible, and the inverse also the first type. Just change k to 1 out of k. And in this case, of course, k is not 0, definitely. Okay. And then let's look at the second type. The second type is interchange 2 row, right? Let's look at this elementary. Okay, look at this elementary. Okay. Oh, sorry, I made a mistake. So here should be 1. See, this is the elementary. Okay, this is the elementary matrix. This elementary was obtained from identity by interchange the first two rows, right? And then what is the inverse? So the same way. So let's do row operation first. Okay, of course, and I will get a identity. It's easy. We just change the first two row back, right? Which is this, the second type of row operation. Interchange the first two row. And now the same, let's write as identity, okay, as elementary. Should be interchange the identity, okay, so by the first two row, right? And that's right. So corresponding to elementary is this, okay. And then this row operation we can change into matrix multiplication by the Theorem 1.5.1. Let me erase this, okay. Otherwise we get confused. And this elementary is corresponding to the row operation. Now, by the same, okay, the same Theorem 1.5.1, we have this. Let me write the equation. Okay, see, and this matrix is the original, okay, and this matrix is just this E. Let's put it E here. This is the elementary. What do we get now? So these two times together get identity. Therefore, one is the inverse of another, right? Okay. So we find the inverse matrix of this, the second type of elementary. Let me write down the answer. Okay. So what do we say? The second type of elementary is invertible. The inverse, see here, still the second type, just equals itself, okay? Now, I look at the third type. The third type, which is by the third type of row operation, let's do this. We add the first row multiplied by k to the third row. Okay, k is not 0. So we will have this elementary. Okay, let me write the elementary as an example. We will try to find the inverse of this matrix, and the k is not 0. Of course, k is not 0. The same. Let's do row operation. How to get identity I 3 by 3. Okay, the row operation should be still the third type of row operation. We can multiply the first row by negative k this time, add to the third row, right? Let me write. Therefore, you can get identity. Now the same, I use the previous theorem to write it into matrix multiplication. So the corresponding identity elementary is this, right? Here's negative k. Now, by the theorem, the same. By the previous theorem, okay, so now I can write it into matrix multiplication, which is this elementary matrix times this original matrix equals I, right? Okay, let me write down. And see, okay, so the first is elementary, okay, so we just have left elementary just equivalent to the row operation. What does this mean? This means the inverse we found, right? This is invertible, and the inverse is just this elementary, okay? So therefore, let me write down what do we have, okay? And this means the third type of elementary matrix is invertible. The inverse is the third type of elementary matrix. Just change the k to negative k. And the k is not 0. Yeah, so that's the verification. Thank you.